In this example, we have a box on the floor being pushed by a bad student. I don't know who this bad student is. We're going to draw a free body diagram for the box, and then we'll answer B in a sec. What we've got then is, let's say here's the floor. So the box is on the floor. Here's a box, and we know for sure there's gravity, assuming that we're on Earth. I think we're on Earth. This is a regular question. We got this box sitting on the floor. What keeps the box on the floor is gravity, but what prevents the box from kind of falling, free falling, is the normal force. So just remember, if one object rests on the surface of another, if my pen rests on the table here, what supports the pen or the pencil, what prevents it from falling is the normal force. Normal force is normal in that it is perpendicular to the surface that we're resting on. Okay, so that's what normal means. Now this student, assuming that the student pushes this direction, let's say, and again, assuming that the motion is this direction, as long as it's moving in the direction that the student's pushing, then friction must be back this way. Remember, friction opposes motion. Okay, so there's our free body diagram. What forces are equal if the box is moving at a constant velocity? Well, from grade 11, you kind of know typically the normal force and force of gravity are equal. That's not always true, and we'll see some examples where that's not true in grade 12. If you didn't see that in grade 11, we'll definitely see it in grade 12. As long as we're on like a level floor, as long as the object is not accelerating up or down, I guess, then those two objects, or those two forces, I mean, must be balanced. They must be the same. If the object moves at a constant velocity, so if v is constant, what that means is acceleration, so let's say velocity is constant, acceleration then must be 0 in order that velocity is constant. If acceleration is 0, you can kind of think back to grade 11. We said F equals ma, net force or sum of F, same thing, sum of F equals ma. If acceleration is 0, then the whole right-hand side is 0. What that means is all of these forces, when I add them up, must add up to 0. Those guys are already balanced. That must mean that this guy is balancing this guy, or maybe friction balances force applied, whichever way you want to say it. Those forces must be equal in order that when I add this positive force and that negative force, I get 0. Let's say that's positive, that's negative, I add them, I get 0. That's what satisfies this constant velocity condition. Does friction always oppose the applied force? Well, I mentioned up here quickly that friction opposes motion, actually not the applied force. Typically motion and the applied force are in the same direction, so typically friction opposes the applied force, but that's not always true. One example that comes to mind is, let's just say, I don't know, Mr. Jack's car breaks down. This is his car. The car is in motion. The car is heading towards this cliff. So here's the cliff. If we wanted to make this a really exciting question, you could imagine there's like water down here, and I don't know, there's a few like little stones kind of falling down. We'll put some little rings in the water. Maybe there's even like a shark down here or something. Hopefully you can see my shark. There's a shark down there waiting to gobble up Mr. Jack, or at least his car or something anyway. Anyways, the car is in motion. The car is sliding down, and Mr. Jack says, oh no, you don't. So he comes over here and he starts pushing his car up the hill. If the car is in motion going down the ramp this way, we would say the free body diagram, Mr. Jack is pushing up this way. Here's his applied force. Gravity is down this way. Normal force, remember, perpendicular to the surface that we're on, so there's the normal force. You can see gravity and normal are not in the same direction. If the motion, though, is this way, then friction has to oppose that motion. Friction must be in this direction as well. So friction opposes motion, not the applied force, not necessarily anyways. It always opposes motion. So if you're trying to figure out what direction friction is, look for the motion. Friction goes opposite to that motion. Let's do a quick discussion about limiting static friction. Static friction is when two objects are at rest compared with each other. So let's say, I don't know, there's a table. You can kind of see all my objects look the same, right? They're all boxes, cars, tables, they're all like big boxes. If there's a box here and I want to get it going, I want to start this thing going, so I'm going to push on it this way, then there's going to be, assuming it's not in motion, there's going to be some friction that opposes that motion, force of static friction. Okay, so this is at rest. At rest. rest. Let's say I push with a force of, 10 newtons. Assuming it stays at rest, friction then also 10 newtons. Let's say, okay, but I want this thing to move. So I say, forget the 10 newtons, I'm gonna push with 15 newtons. Assuming it remains at rest, friction also changes and goes to 15 newtons. Let's say I really get serious now and I push with 20 newtons. Again, assuming it's at rest, friction ups the ante with me. It always matches my force. Assuming it stays at rest, friction always matches my force and goes up to 20 newtons. They're always balanced. Now, let's say that is what we call this limiting static friction. So if this is FFS, and I'm going to put lim down here, there's a lot of subscripts, but subscripts on subscripts. If this is the force of limiting static friction, okay, so there's a lot of subscripts. If that is 20 newtons, then that's the maximum force that this thing can resist with. So if I say, all right, forget that, I'm going to go up to 21 newtons. Friction can't resist with any more because that's the limit. So friction is this variable force. It can change with whatever I push with, but it cannot go bigger than the limiting static friction. If I push with 21 newtons, this thing is no longer at rest. The object moves, the desk or whatever it was I said it was, then the object starts to move because my force, my applied force, is greater than the force of limiting static friction. When that happens, the object starts to move. Once it starts to slide, I actually no longer have static friction. Then I would start to have kinetic friction. Kinetic friction is always less than the limiting static friction, so I'm just totally making up numbers here. Maybe it's 17 newtons or something like that. Then we could use our F equals ma and start to figure out, what the acceleration is or whatever we want to figure out.